Video for April 28th. We're going to be talking about the probability of an event today. Alright, so our do now asks us, imagine a pizza place that has 10 different possible toppings. How many pizzas are possible? Ranging from a completely cheese pizza with no toppings to one where you put all 10 on. So to figure this one out, this is a counting problem. We have to put all 10 of our toppings in order, and we have to ask, am I including this topping or am I not? And as I add an additional topping, it doubles the size because we can do all the previous pizzas with that new topping or without that new topping. So it can be either on the pizza or it can be off the pizza. Those are two possibilities for each topping. So we're going to do 2 times 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 2, or 2 to the 10th pizzas. And 2 to the 10th is 1,024 pizzas. Alright, how many of those have 4 different toppings? So we could go yes, no, 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 yes, no, no. That's a possibility. How are we going to add those all up? Well, we're going to do a combination. This is a combination because order does not matter. It doesn't matter if you put on the pepperoni first, then the pepper, or then the jalapeno. So how many toppings do I have to pick from? 10. Do a combination, so I use a big C. So 10 choose 4, 10C4. And the math for this is you do 10 factorial divided by 6 factorial times 4 factorial. Or I'll just do 10, go over to probability, NCR4 in my calculator, and I get 210 of those pizzas have exactly 4 toppings. Alright, this can get more complicated if we allow the option for doing like double of a topping, or if you want to have like the arugula added on after, make this problem as difficult as you want. Alright, goal for today is to be able to determine the sample space of an experiment and find the probability of an event. Why? Well, there's so many applications to this. Every time you make a decision, you're kind of making a bet, and all of those bets are based off of probability. And the amount of reward should be based off of how rare an event is. So if you want to know if you're making a good decision or a bad decision, you got to understand probability. If you want to follow along in your textbooks, it's page 435. Get your notes, put today's date at the top. Here we go. A few definitions. What is a probability? What is a probability? I think we all know what this word is. How do we define it? Well, a real key feature of a probability is that it's numeric. It is a number. So it's a numeric representation of the likelihood of an event. A numeric representation of the likelihood of an event. An experiment. Well, in terms of probability, experiment has a very specific definition. The experiment is when an outcome of a probabilistic event is observed. All right. So every time you shoot a basketball, you're doing an experiment. Will it go in? Will it not? That's based off of probability. An outcome are the unique results of an experiment. All right, so it could be just what does the die say when it is rolled, or what card do you draw on a deck, or whether or not a basketball goes into or does not go into the hoop. All right, the sample space. Sample space are all of the possible outcomes of an experiment. All right, and they can be combinations. So sometimes we're flipping a coin and we want to know how often heads comes up. So we need to do the sample space of all possible combinations of three coin flips. All right, and an event. It's very similar to an outcome. I'm gonna look up a more precise definition here. Give me a second. Okay, I found a definition of event that I like. It is a subset of outcomes. So maybe the outcomes are all of the different ways to draw a card out of a deck, and the event is, we want to get a full house, or we want to get two pairs. So there might be a lot of different ways for an event to happen, and you have to combine different outcomes to make sure you cover all of them. Okay. The probability of an event. So, in order to calculate the probability of an event, the first thing you have to do is assume all, we'll say, outcomes are equally likely. So assume all events are equally likely. So this might not always be the case, and there's ways that we can deal with it if it's not the case. But when we're like rolling a die or drawing a card out of a deck, we're assuming every card has an equal chance of being picked, because the deck has been shuffled, or we rolled the dice with enough momentum that's not just going to land flat. It's going to roll around, and then it just becomes every number is going to come up equally. And then to calculate the probability of an event, the probability is the number of ways an event can happen so the number of outcomes that satisfy the event divided by the sample space, which is all of the possible outcomes. So we say this is how it's written. So the probability of some event E is equal to the number of ways E can happen divided by the size of the sample space of our experiment. How do I want to write this? another quick pause, make sure I'm getting my notation right. Okay, I was doing this a little bit wrong. For the size of the sample space, you do the number of elements in the sample space. There, that now matches our definition on page 436. All right. How to convert a probability to a percent. So if we've got the probability of some event E, to turn it into a percent, we multiply it by 100%. Very simple. So probabilities are always going to be between 0 and 1. So for how do we represent an impossible event? Impossible means we have a probability of the event being equal to 0. All right, and then a certain event means the probability of event E is 1. And then all other probabilities fall in between those. So the inequality we can write because of that is that 0 is less than or equal to the probability of any event E, which must also be less than or equal to 1. This is always true. It's impossible to have a probability of 200%. It just doesn't make any sense. All right. So, two coins are tossed. What's the probability that they both land heads up? So to figure this out, we got to figure out, so the probability of heads is equal to the number of ways we can get heads divided by the number of ways we can flip two coins. All right, and the number of ways we can get heads, there's only one way to do that. Get heads in the first, heads in the second. Number of ways we can flip two coins, well, let's see if we can list them all out. We can do heads, tails, heads, tails, tails. So there's 4 different ways that can happen. So it's a simple 1 and 4. All right, if you do this experiment over and over, most often or half the time you're gonna get 1 heads and 1 tails. Then a quarter of the time you'll get heads, the other quarter of the time you'll get tails. All right. A card is drawn from a deck at random. What's the probability that it is a 7 or a heart? Probability that's a 7 or a heart. So how many ways can we get a 7 or a heart? So the number of ways to get a 7 or a heart. Let's see if we can list them all out. So we could do the ace of hearts, which I'll just call 1H. We can get the 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, 6 of hearts. Here, I'll pause to list these all out. All right, so we've got 13 different ways to get a heart. Now how many ways can we get a 7? You can get the 7 of diamonds, the 7 of spades, the 7 of, what am I missing? Clubs. But the 7 of hearts is already in this list, so we don't want to write it out twice. No duplicates in here. There's only 1 7 of hearts. It counts as both a 7 and a heart. So how many items total are there here? Well, there's 13 ways to get a heart plus 3 more ways to get the 7 for a total of 16. Now how many ways can you draw a card? Well, there's 52 different cards in the deck. So now we do 16 divided by 52. And we see that if we need a 7 or a heart, we have a 30.7, well, I'll write it as 0.307 7 chance. That's our probability expressed as decimal, or a 30.77% chance. So either of these would be an acceptable way to report that probability. All right, call that good for this lecture video, and have a good rest of your day.